MERL's new seminar series to introduce Ruohan Gao, who's currently a postdoctoral scholar at Stanford University. And Ruohan's work initially came into my attention when we were brainstorming ideas of neat things we could do with audio-visual multimodal processing. And I thought I had this really great idea about using video to help make like a spatialized stereo mix. And someone said, oh, you should see this paper from Kristen Grauman's lab. And Ruohan was the first author. I read it. It was a really exciting paper. There were many others, and been a big fan of his work ever since. So I was grateful when we wanted to invite emerging researchers. He immediately popped into my mind. And so a little bit about Ruohan, that in addition, that work that I mentioned about the 2.5D visual sound received a Best Paper Finalist Award at CVPR. He also received a Google PhD fellowship and an Adobe fellowship during his PhD, and which he finished last spring, and he won the University of Texas Best Dissertation Award for his work. So with that, let me introduce Dr. Ruohan Gao.
Yeah, thanks, Gordon, for the very kind introduction. Yeah, hello, everyone. Thanks for the kind invitation. It is my great pleasure today to be here to tell you something about our past research on how we open both our eyes and ears to perceive the visual world. So as all of you know, there has been significant recent progress on visual recognition in the last decade. Now, given an image like this, we can do lots of cool stuff. We can recognize this is a living room. We can detect the objects, recognize it's a dog, it's a baby, or even segment them out. We can also do 3D reconstructions of the objects in the scene. So despite the encouraging progress, actually 60 years after the first digital image was introduced by Russell Kirsch, we are still working hard on trying to make sense of the visual world. So what has made vision such a hard problem? So let's first look at how vision comes into being in the first place. So for us to see this image, there must be a light source, for example, a bulb in the room. So it's emitting light rays in all directions, right? So let's just consider one light ray for simplicity. That light ray goes into the scene, hits the surface, and then bounces off in all directions. Then each reflected light ray hits other surfaces, creating such chaos. And then maybe outside this image, there is a receiver or camera that receives reflected light rays. And computer vision is to make sense of the visual world built from all these light rays. And it's amazing how we humans can make sense of what we see just from these intertwined light rays. And for a machine, it's absolutely a hard problem. But are we missing something here? So let's go back to this image and see what's really happening here. Okay, as you can see and hear, right, our visual world doesn't only consist of a bunch of light rays. There's also sound. And when the baby laughs, it expels air from its lung and pushes it through its larynx or the voice box. And then the vocal cords vibrate, causing the laboring air particles to vibrate and generating sound waves. And these sound waves bounce against all the surfaces in space, and the dog might be also barking, generating more sound waves. And similarly, out of the view, there might be a microphone receiving the sound waves, and the diaphragm in the microphone also vibrates, generating the sound signal. So as all of you know, there is also a large audio community trying hard to make sense of the mess of sound waves. So what if we put all these signals together like this? Actually, if we open both our eyes and ears to perceive the world, things become much easier because the perception of the two modalities are mutually beneficial. And most of my past research is focusing on using both the visual and audio modalities to understand our visual world. Particularly, there are things that can be done using vision alone that might be much stronger once we're able to listen. For example, the sounds of the natural sound makers, like a cat, can tell us who they are based on the sound they emit. Sometimes the object itself might not be a sound maker, but once it bangs against other objects, it reveals something about the materials. And there's emotion, people's emotion can be told from the sounds they make. And dynamic sources, something that draws our attention, might not be the object itself, but maybe an event that happens to it. And maybe there's a sound that accompanies this event. And of course, there's conversation. What is being said naturally helps us to understand the speaker. And our everyday activities are also accompanied by various sounds. An ambient sound in the environment can tell us something about the space and where we are. So therefore, there are many things that we can capitalize on. And particularly in my talk today, I'm going to mainly talk about two ideas. So first, I'm going to talk about how we use audio as a semantic signal and use it for audio source separation and action recognition. Secondly, I'm going to talk about the spatial signals in audio. So what we hear not only can tell us what the objects are, but also where they are, right? So first, we study how audio can serve as a semantic signal in audio-visual learning. Human development learning is actually also a multimodal experience. Kids can quickly amass a repertoire of objects and their sounds. Similarly, our goal here is to learn a representation of what different objects sound like so that we can have a joint model of how things look and how things sound. But the challenge is that in real world, the sounds of different objects does not exist in isolation, but are usually mixed together in various scenarios. In an unlabeled video, object sounds often exist as a single audio channel that mixes all of them together. So the problem is how we can obtain these object sound models naturally, including from unlabeled video. So particularly, I will talk about our recent work on audio-visual speech separation as an example. So it's related to the famous cocktail party effect, as many of you definitely know. So for decades, scientists have puzzled over how our brain is able to focus on certain sounds while filtering out others, just like someone in a noisy room with many different sound signals around, he can easily focus on a single conversation. So we have this remarkable ability to focus our auditory attention on a particular stimulus and separate it out from a range of other stimuli. So we formulate this problem as visually guided speech separation. So given a video, we first split the video into its audio stream and the video stream. And we detect the visual objects, like the speakers, the faces in this case, and the use of visual information to guide the separation, to separate their voices respectively. Actually, several recent work have tackled this problem. So these prior approaches all focus on learning the alignment between the speaker's lip movements and the sounds they generate. We observe that the consistency between the speaker's facial appearance and their voice is also revealing for speech separation. So I'll give you an example here. Here I'm showing 5 faces, and I'll play the voice of one of the speakers, and you can probably tell which speaker the voice is coming from, like this one.
Moi je suis une novice, pour le coup, j'ai jamais vu ça concrètement, mais c'est 2 mois.
This might be a very extreme case, and you can easily tell the speaker based on obvious reasons. And how about this one?
People being cool, and you can see that in daily life.
Probably can also tell it's coming from the 4th speaker, right? So a person's gender, age, nationality, or even body weight are often visible in the face, and it can give a prior for the voice qualities. So, for example, female speakers often register in higher frequencies, and research also shows that a heavier person may exhibit a wider range of sound intensities. Suppose if we have a cross-model embedding space and we want to embed the faces and the voices of these speakers, so the face And the voice of the second speaker should be embedded closer in the embedding space, and the voice of the fourth speaker should be embedded closer in the embedding space and further away from the second speaker. Right. So actually, prior work on cross-modal matching exactly learns this kind of cross-modal face voice embeddings, but for the purpose of person identification. Differently, our goal here is that we want to do audio-visual speech separation. And we find that these two tasks are mutually beneficial. So the better audio-visual speech separation, it will create better separated voices, leading to distinctive voice tracks that can help cross-modal embedding learning. And the better the separated sounds, it can also create better vocal and facial prior, which can help separation. So these two tasks are mutually beneficial. So our idea is that we want to jointly learn audio-visual speech separation and cross-modal face-voice embeddings. So given a speech mixture of like two speakers, we want to use a visual information to guide the separation, so we get the lip motion information and the face embedding for the first speaker, and we combine the lip motion cues and the appearance cues, the face embedding, and we can use it to guide the separation to separate the voice of the first speaker. Similarly, for the second speaker, we can extract its lip motion to get the lip motion cues, and we can get its face embeddings, and we extract and combine these two cues and to guide the separation to separate the voice for the second speaker. And simultaneously, we also do cross-modal embedding learning. So the embedding of the separated voice for the first speaker and the face embedding that was originally used to guide the separation, they should be embedded closer in the embedding space. Similarly, for the face embedding and the embedding of the separate speech for the second speaker, they should be embedded closer in the embedding space. So we want to pull the embeddings of the same speaker together and push the embeddings of different speakers away in this cross-modal embedding space. And we do this jointly for audio-visual speech separation and cross-modal face-voice embedding learning. And so the embeddings serve as a prior for the voice characteristics that can enhance speech separation. And the cleaner the separate speech in turn produces more distinctive audio embeddings. So here is an architecture of our audio-visual speech separator network. I want to go to the details. This is trying to separate the voice for one speaker by combining it leverages the complementary visual cues of both the lip motion and cross-modal embedding to guide the separation process, and combining the lip motion features and face embedding features and using a unit architecture, and we can guide the separation to separate the sounds for this speaker from the mixture sound. This is for one speaker, and remember, our idea is we want to do multitask training. We want to do multitask learning to jointly learn audio-visual speech separation and cross-modal face-voice embeddings. So basically, here we have a framework to do this multitask training, and we have the two speakers. We want to do the separation jointly. We also have this cross-modal matching loss, trying to learn the cross-modal embeddings, and jointly we find this trying to also help cross-modal embedding learning and also help audio-visual speech separation. So I will skip the details here, and let me show some results of our framework. So here, first I'm going to show the original mixture where two speakers are speaking simultaneously, and then we are trying to use our system to separate their voices respectively. Here is the original video where two speakers are speaking.
No, you became a superstar.
No, I did not.
Yes,
no,
you
I
did.
did not. No,
sure
I did
you
not.
did. From
Are
me,
you gonna
I
let
gave
me
you full
speak my
credit.
piece?
If you're talking to me now,
am I gonna
I
speak
gave
my
you full
piece?
credit for that.
Am I gonna speak my piece or not?
Go
Am I
ahead.
gonna speak my piece or not?
Go ahead.
Okay, because you want to interview me. I ain't interviewing you. You want to talk to me. I don't worry about talking.
Floyd,
You want to
go
talk
ahead.
to me.
I'm waiting on you.
All right. So now let's separate the voice for the left speaker.
Well, you became a superstar. Yes, you did. Sure you did. From me, I gave you full credit. If you're talking to me now, I gave you full credit for that. Go ahead. Go ahead. Floyd, go ahead. I'm waiting on you.
And the voice for the right speaker.
No, No, I did not. No, I did not. No, I did not. Are you gonna let me speak my piece? Am I gonna speak my piece? Am I gonna speak my piece or not? Am I gonna speak my piece or not? Okay, because you want to interview me. I ain't interviewing you. You want to talk to me. I don't worry about talking. You want to talk to me.
You can see that it works pretty well. So we can also adapt our model to do audio-video speech enhancement. So where the task is we want to separate the voice from the mixture audio, where there's some background noise in the mixture. So here is original video with background noise.
So today's talk, communication behaviour strategies, we're going to talk about over a couple of videos because there's actually quite a few tips and tricks to get through to help people with normal hearing and people who have a hearing loss or are hard of hearing. Yeah. So what are some of your tips and tricks for people who come to a noisy place like a cafe cat?
So our tips and tricks will be to use our system to do audio-video speech enhancement. Now here is enhancement speech.
So today's talk, communication behaviour strategies, we're going to talk about over a couple of videos because there's actually quite a few tips and tricks to get through to help people with normal hearing and people who have a hearing loss or are hard of hearing. Yeah. So what are some of your tips and tricks for people who come to a noisy place like a cafe cat?
Okay. Here are some quantity results. We compare to prior state-of-the-art methods, audio-video speech separation and audio-video speech enhancement. And we can see that on the standard benchmarks, our method improved the state-of-the-art on all 5 data sets. All right, so this is for audio-video speech separation. So apart from speech separation, our prior work also studied other objects such as musical instruments. Here I'm going to show you an example of our work where we train over 100,000 unlabeled multi-source video clips, and then we try to separate audio for a label video for a mixture of musical instruments. So here is one video of a violin and a flute. Here's a mixture audio. And let's separate the sound for the violin. And the sound for the flute. Okay. If you have any questions, feel free to interrupt me anytime. Yeah, I'm happy to answer any questions during the talk. So yeah, what I showed just now are all sound mixtures in videos. So the final kind of source separation example I'm going to talk about is our latest work called Deep Impact, so which can be used for source separation for robotics tasks. So a robot can often interact with different objects with a tool. So the sounds an object makes when impacted can also inform a robot about its material properties of the object. And these material properties might not be very evident from vision, but these properties can be important to assess the strength or durability of this object. And this information can be very useful if the robot wants to grasp and manipulate the object, right? However, when the tool and the object strike each other, as you can see here, the resulting sound is actually some composition of both the sounds made by the tool and the sound made by the object itself. So how can a robot differentiate between these two sounds? This is also source separation. So to do this, we actually propose a model called Deep Impact. This is a general model, but we have kind of applied it for source separation tasks. So this Deep Impact model is a differentiable model for rendering impact sounds of rigid objects. So it uses physics-based models for modeling different physical characteristics of the impact sound of an object. So you can see there are different modules which interpretable physically interpretable modules, and by combining these physics-based model bias with a fully differentiable renderer, we're able to use this deep impact model to infer physically interpretable parameters from real-world sounds, such as force profile, like the model impulse response for objects, noise, reverberations. So this is our full model. I will skip the details, but on a higher level, we use an analysis by synthesis process to fit an acoustic model to each object. So for example, taking a ground truth spectrum as input to the deep impact model, we hope to model the impact forces as well as the impulse response of the striked object from the ground truth spectrum. This is coming from a recording of a real robot interaction. And then we combine the impact force and the impulse response, and we can try to synthesize the waveforms. Then we can get a predicted spectrum from our deep impact framework. Then we can use a loss. So like we have used an L1 multi-resolution spectrum loss to optimize through this fully differentiable framework. Then we can try to fit this acoustic model to learn the impact forces, the impulse responses from this deep impact framework to fit the ground truth spectrogram. So that we can actually fit acoustic models to each object from sounds of multiple pairwise impacts between different objects and tools. It can then use the acoustic models it learns to separate the sounds of these objects from each impact sound. So here I'm going to show some a sample result from separating the sounds from a steel fork and a ceramic mug. So the fork has higher pitched, underdamped components, whereas the mug here has a slightly lower frequency components. So here is a video of the strike. The directionality and the gain of the microphone already can get rid of most of the noise. But there is still some robot motor noise. You can actually see a faint band across the spectrum here. So after our model has fit parameters to this audio clip, here is a synthesized output for the impact. Let's hear it again. This includes all the sound components except the background noise. The background noise models the sounds such as a motor noise from the original recording. And since our model has composed its sound by fitting acoustic models for both these objects, the steel fork and the ceramic mug, and then we can turn off the mug's contribution and isolate the fork contribution to get only the model's estimate of the fork sound. And here is a sound for the separated fork. And we can do the same for the mug sound. Thus, we can successfully separate the sounds for these two objects using our deep impact framework. So to show how this separate object and tool impact sounds could help a robot to make useful inferences about the object, we have done experiments to show that these separate sounds can actually help the robot to classify the material from audio. As I mentioned, sounds an object makes during impact and manipulation can be very informative of what material the object is made of. And this can be very important for judging how to manipulate and grasp the object. And here we show the results of using a classifier which uses audio of impact sounds to classify materials of objects. And our model helps to improve the accuracy of classifying the material of each object from the sound of their impact, significantly from just using the original sound of impact, and also significantly outperforms the source separation based like the non-negative matrix factorization and deep audio prior. Okay.
Hey.
Okay.
Ruohan, before we go on, we have a question from Chiori.
So Ruohan, thank you very much. So let me ask one quick question. So if you use the visual information only, can we perform how much we can classify the materials.
Oh, you mean for
visual information only, audio information only, like. So did you do the ablation study without one of the features?
Yeah, that's a good point. Yeah, I think in this experiment we haven't explicitly done visual material classification. Yeah, but I think that's a good baseline. Yeah, here we only we are trying to use material classification kind of as a proxy to see how the sounds, the quality of the separate sounds. So we haven't explicitly done visual classification, but I think that will be an interesting baseline. But I think some of the material actually are pretty hard to distinguish based on my intuition. Audio sometimes can actually better distinguish it, but this is just kind of hypothesis. But the reason we want to do material classification using separate sounds is that because this is kind of different from traditional audio separation, because in a lot of like learning-based source separation, they usually have the clean audios for each object, and they want to mix them together using a mix and separate framework, trying to learn how to separate the sounds for each. But in this scenario, actually, when you use a tool to kind of interact with objects, you never have the ground truth of the individual components of the object. So that's why we cannot evaluate it. So that's why we use.
So, yeah, actually, I agree with you, strongly agree. I support you. Just we really need to know the fact for this experimental setup. We have a very good object recognition tools. Visually, we can recognize, mug cup is a kind of, we can predict, material. But sometimes, outlooking doesn't match with the real materials. Definitely your research works good. And just to, let us know, you're using, object recognition features and that actually give an impact, how much that part gives an impact on this, experiment. That I want to know. Okay, so thank you. But I strongly support your experiment.
Yeah. A final comment on this. I totally agree. I think visual information most likely actually is very useful. Is sometimes more use. I think most likely it's more useful than audio in most cases. And maybe there are some materials that's hard to distinguish using visual information. Audio can help. But actually, I think probably the most interesting application scenarios for audio-based material classification is that when there's like low lighting or kind of in dark environments and robot want to interact with objects, so we cannot use visual information, so we can only use sound. Or maybe some objects are occluded, we can do interactions, so we can still distinguish the materials, but we don't have visual information. So probably in that case, it would be more useful for audio. Yeah.
Thank you.
Yeah, thanks for the question. Yeah.
Okay, Tim also has a question.
Yeah, hi. This is very cool. I love this idea of separating when you don't, for these objects, when you only get them sounding at the same time. But that does bring up the question of how do you know how well you're actually doing the separation, because you don't have ground truth. And so how do we know that, in those sounds you played of the mug and the fork, that especially in that initial sound, at the beginning, you weren't getting sort of both sounds from both of them, and then maybe later on in the sound it got separated better. I mean, is there any way to know how well you're doing? Can you use synthetic models of the sounds of the individual objects to see how well it separates, or is there some other way you can really tell how well you're separating the whole sound?
Yeah, that's a great question. I think evaluation in this scenario where we don't have the ground truth is very hard, right? So this is one of the ways, the one proxy to evaluate whether the separate sounds are successful or not by material classification. Actually, we also did some user study trying to compare with some baselines, trying to see because users, we can tell whether it's the right material. So based on,
I'm not so sure about that. I don't know if I've ever heard if I could separate a fork and a mug and know exactly which part was which, but go ahead.
Yeah, I think user study is also like a proxy way. Yeah, that's the two ways we use trying to distinguish whether the separate audio is correct or not, based on kind of intuition or kind of common sense of the user or humans. But I think I agree with what you said. Maybe there are definitely a lot of difficult materials. Probably humans cannot even tell. Maybe synthetic approaches can be used here, trying to as a reference.
Could you go back a slide or two to where you sort of showed the different parts that go into the there. Which parts of this, so I assume you've got like multiple forks hitting different things and multiple mugs being hit by different things, and that's part of how you're training the separation, is that it can learn, you know, what a mug sounds like from multiple different cases of mugs mixed with other things. Is that right?
Yes and no. Yeah, this is basically, I showed the separation examples, but actually this is a deep impact. This is a general framework. Actually, we are not doing separation specifically. It's kind of a general kind of differentiable impact sound renderer, which can take an audio spectrogram and trying to fit this physically interpretable parameters for the impact sound. So for we can adapt this framework for source separation. Basically, we just fit these parameters for two objects, like one tool, one impact. Then to learn two sets of parameters, then we can do the separations, which I don't think I showed here in this figure, but yeah.
Yeah, I guess what I'm wondering is, you know, this is someone else's framework for one object, right? And you're combining it to be this sort of combination of two different objects. What, you know, when you have multiple forks, what's the part that you assume is the same each time the fork is used? Do you assume that the I don't know, that the impulse response is the same, but the force is different? You know, what is it that you're assuming is the same across all forks? And what is it that you're assuming is different?
If it's multiple forks, I don't think it's going to work. If it's different objects, they have different object impulse response.
Okay, so against about the same fork every time you use it, what is it that you assume that's the same, and what's allowed to vary in this picture?
In this, the force profile will vary. For example, in this figure, we can see that basically we are trying to fit
right
the impact force and the impulse response. The impulse response is object level. Basically, it depends on the material, the shape of the object, right? And the impact force is based on inferring from the real recordings. These are the impacts. We can infer a impact force profile based on the recordings. And
so
the
impulse response is what's constant across every time you use that fork, no matter what you're hitting, basically.
Yeah, exactly.
So I guess one way you could see how well it's working is how well your separated explanation matches the ground truth combined sounds for all of the different combinations.
Right, kind of like we combine them back to see whether it matches the original recording. Yeah, that's a good point. Yeah.
This is excellent. Thank you.
All right, Matt.
Hey, this is fun, and if I remember correctly, your academic grandfather, Trevor Darrell, worked on something like this with Paul Viola, using mutual information between audio and video a while back. And I wonder if this has a similar property to that work, in that your examples seem to have interesting separability properties. For example, your speakers are well separated spatially in the frame, and for example, if you're coding motion, any kind of motion as your input feature, it's going to correlate with different features in the spectrum. Different features in the video frame are going to correlate with different features in the spectrum and be nicely separable. And also for this impact stuff, maybe it's this particular example, the fundamental resonant frequency of the mug is a good deal lower than that of the fork. So again, there's good separability in the spectrum. So would this stuff work, for example, if the camera and the microphone or microphones are moving as they would be if they were mounted in a real human head? Because that will remove your spatial separability. So for example, if we put the camera and the microphones in a human head, which is moving, then your visual features aren't in the same part of the frame. They're moving around in the frame because the perspective of the head is moving. And similarly, the the phase relationship between the two sources is changing if the essentially the view angle is different. So I wonder how much the system is learning to exploit the actual geometry of your capture.
Yeah. So yeah, I think basically, if I understand the questions correctly, yeah, I think basically there are two questions. One is more about how we use visual information to get the separation. Yeah, I think that, like you mentioned, there are some prior work. Yeah, maybe pre-deep learning stage. And we also have this, can maybe use some statistical analysis trying to analyze the correlations between the visual and audio components to do the separation. Now here we are basically, we have different ways we extract the visual information, use the visual information to guide the separation. And here, particularly in our work, we are mostly leveraging the semantics of the objects, the categories, to guide the separation, and to learn the kind of frequency basis, trying to see what kind of sound each type of object makes, use it to guide the separation. There are work trying to leverage motion, like you mentioned. Maybe when I play violin, maybe the correlations of the hands can kind of, how you move your hand can also be useful for separation. And I think for a second, the spatial aspect, if I understand the question correctly, you were saying if you're moving, if I'm not sure I understand that question correctly, because we are focusing on single channel audio source separation. It's not spatial audio, it's not binaural audio. So,
well, you get spatial information from the location of the two sound sources in the video frame, and also from the fact that there are different distances from the microphone. So you have a phase, you have phase information there.
Right. Yeah, I think that's something we haven't looked at, and that's something I think it will be especially useful if we do like binaural audio source separation, which we currently actually focus on single channel audio. I think maybe that factor is not that important, or we cannot leverage that factor very well. If we do binaural audio source separation, probably I think that would be more easy to exploit if I understand correctly.
Well, my question is flipping that on its head. So in the mutual information studies that Paul and Trevor did, it turned out one microphone and one camera was enough because there was good spatial separation in the scene. And there was really no learning. It was a purely statistical analysis of the waveform and the video signal. So what I'm asking is, if we were to have the camera and the microphone in motion as you do the capture, that's what destroys a lot of this easy to exploit correlation. And I wonder how robust your results would be.
Yeah, so the correlation we're exploiting is less on that side. It's more on the semantic side. So basically, we are exploring, even it's kind of moving, it's in different kind of places. Maybe the phase will change, but we're exploring actually the category information. We are leveraging the prior learn from like unlabeled videos. In videos, we learn this instrument can play, usually can sound like what kind of sound, and then we're trying to match the categories. So this will not change. So I agree that is another factor we can explore. We're not doing like this kind of correlation based or statistical analysis in that sense.
Well, the network may be. The network may have learned that that's the easy way to train, essentially, to exploit those properties of the signal in order to match the semantic content of the training data.
Right, but for example, in one of our, we only used object detections, so we don't even know the locations of the objects actually. So we only leverage these like the object categories, object detections, trying to guide the separation.
Oh, so the system doesn't know anything about where
spatial.
The motion is happening in the video frame?
Right, because we are doing static frame. We are not doing like temporal information in our.
Really? So yeah. for the early videos with the speakers, it's all static. The video analysis.
For the speech separation, it's not static, but we are basically it's only a face, right? It's only a face. We never have the full picture of where the person is standing in the space. We only have the faces, so we only have the face tracks. and we have the leap motion. So that's only temporal information. So there's nothing we can exploit about the locations in the 3D space for the speakers.
Not in the 3D, but they're in different locations in the video frame, and that can be correlated against the phase difference at the microphone.
Yeah, but that's something we're not exploiting in the video information. We basically just extract the phase tracks and use the phase tracks to guide the separation.
Okay, but it does have that information. Okay, and what would happen if we were to do a toast and clink two mugs together? Maybe a glass mug and a ceramic mug of similar size, so they have similar fundamental frequency.
Yes, I think in that case, I don't think our current model can handle that, because it's basically it cannot. Maybe we can still fit the.
They have different harmonics.
They have
different shape.
Yeah.
There's a nice theory. There's a conjecture and harmonic analysis that you don't need vision. You can reconstruct the shape from the sound.
Right. Currently, our object impact. I think it's definitely a good extension. But currently, we only model the materials. We didn't model the shape. Basically, we are modeling the materials of the object for the impulse response of the object. So, of course, it also in one of the work I'm going to introduce later, we consider shape in model analysis, trying to see how different objects will sound like based on the shape, material. Yeah.
Okay, all fun. Please continue.
Okay, thank you. All right. So yeah, so now I'll continue. Okay, just now I talked about how we use the semantic signal in audio on an audio task, audio-video source separation. So can the semantics in audio also be useful for vision tasks? So next, I will talk about our work that use audio as a semantic signal for action recognition. So this is a classic problem in computer vision. So given a long untrimmed video like this, there is high temporal redundancy across clips. Many clips capture the same event repetitively. And secondly, there's also redundancy even within a clip. Temporal adjacent frames are usually visually similar. So to recognize the action in a long untrimmed video, most methods design a powerful and clip level model and then densely apply the clip classifier and aggregate the prediction scores of all the clips across the video. So this approach becomes computationally impractical in real-world scenarios where the videos are untrimmed and span several minutes or even hours. So therefore, our goal here is that we want to do both efficient and accurate clip level and video level action recognition in untrimmed video. So our idea is that we want to use audio as an efficient video preview of the accompanying visual content. So on the clip level, instead of the costly processing of all frames in a clip within some expensive 3D CNN network, we want to replace it with a more efficient processing of image audio pair. And we want to do this for every clip. So our insight is that a single image captures most of the appearance information within a clip, while the audio provides important dynamic information. And we achieve this through a cross-modality distillation step. Given the original video clip, we use a powerful but expensive video clip network. We extract a video embedding from this video clip. And then, for example, given the starting frame of this video clip, we can use an image network, trying to get an image embedding. And for the accompanying audio of this video clip, we can get the audio spectrogram and get pass this through an audio network. We can get an audio embedding and combine these two embeddings. We can get an audio video embedding. And we treat the top model as a teacher model, the bottom model as the student model. Then we can distill the knowledge from the teacher model to the student model. So at test time, we only need the student model, which is much more efficient than the teacher model and has also good performance. So then we can replace the costly analysis of video clips with more efficient processing of image audio pairs. So the clip level preview step replaces the processing of high-dimensional video clips with a lightweight model analyzing compact image audio pairs. But not all the image audio pairs are needed to recognize action. Instead of classifying every image audio pair with high repetitive information, we iteratively select the most useful image audio pairs. So we designed a video skimming module to achieve this. We also do this by previewing audio. So our video level preview step uses an attention-based LSTM network to interact with a sequence of image audio pairs. So at a certain time step, we use the clip level image audio network I just showed from the clip level preview module to extract an image embedding and an audio embedding for the current clip. And we can combine this image feature and audio feature to get an image audio feature, passes through LSTM, and we can predict an image query vector from the hidden state of the LSTM to query the sequence of image indexing features from each clip, extracted from each clip across the video. And we can predict where to look at next. And similarly, we can also predict an audio query vector to query the sequence of audio indexing features extracted from each clip and predict where to listen to next. So this is for step T. And then we can get the new image and audio features for the next time step and continue the recursive process. And finally, we can select a subset of key moments, a subset of these image audio pairs to perform efficient video level recognition. So we iteratively predict where to look at and listen to next to select the key moments for efficient video level recognition. And during training, we iterate for a fixed number of T steps. And if at inference time, we can stop early at any step, just depending on our computation budget. So here I'm just going to show a key result that we have. So the x-axis here shows the computation cost in G-flops, and y-axis shows the mean average precision. So we compare our approach to state-of-the-art frame selection methods given the same computation budget for untrimmed video action recognition on ActivityNet. So these methods are either guided with strong human supervision or use reinforcement learning approaches to select the keyframes from the untrimmed video. So you can see that our method consistently outperforms these existing frame selection methods and achieves the best balance between speed and accuracy. And our best results is obtained with the use of both the clip level preview and video level audio preview. Okay, so this is for action recognition, where also we use semantic signals. And what I have shared so far is all about semantics, in the sense that we are learning about objects and the sounds they make, and how we can leverage it to recognize actions or separate their sounds. So then the rest of my talk, I'm going to focus on another aspect of audio. I will talk about how we use audio as a spatial signal. So imagine you are inside a forest. So listening to a bird sing a nearby tree, you can relatively quickly identify its approximate location here and attend to it. Okay. So why we can sense the spatial location? There are two key factors why we humans or an embodied agent can perceive spatial effects in audio. Firstly, there are factors in the 3D environment. So there's geometry of the space, there are material properties of the surfaces, and the position of the source and the receiver. These are all going to affect what sound the agent receives. Secondly, there are also factors related to the agent's embodiment itself, which also contributes to the spatial effect in audio. So with humans, we use 2 ears to extract sound sources from a mixture. So the two signals enter the left ear and right ear separately. This will cause a spatial effect. So there are 3 main cues: the interaural time difference. It comes from the different pass lengths around head. Interaural level difference. It comes from the head shadowing of the far ear. And the pinna reflections also change spectral detail. It also contributes to spatial effect. So that's the reason why we can sense spatial effect in audio. But how can we leverage sound in 3D spaces? So what we can get from sound? Certainly, we can actually open up the chance to navigate to the sounding objects. For example, maybe there's a phone ringing in the bedroom in the 3D space. We want to navigate to the location. So we can also use sound to understand activities. So each activity often has a unique sound associated with them. The sound is also a fundamental cue about the semantics. If the agent at the bottom of the scene hears maybe water running in a given direction, then maybe it can tell us about the objects or the things, or maybe the room might be there. So we also have explored the task called audio view embodied navigation, which is tackling something like this. And there's also sound can also inform us. It's also added a signal about the geometry and material properties of the space. So what I want to show next as an example is how we use echolocation to learn about the geometry of the 3D spaces. So to motivate, so what is echolocation? I want to first look at this clip from a famous movie called Daredevil. So the main character, Matt here, he uses a stick to create sounds and receives echoes to perceive the scene. As you just saw, although Matt is blind, but he used a kind of heightened reader sense that allows him to see just by listening. So he uses echolocation kind of to locate the criminals as shown here. You can notice that the sounds produced by the clip causes a lot of reflections and reverberations from the surfaces, and this conveys about the geometry of the environment and the locations of these objects. So actually some animals like the bat, dolphin, and whale, they have remarkable echolocation capabilities. And even visually impaired people, they can also find their way and locate objects by producing mouth clicks and trying to sense and listen to the return echoes to sense the directions. So they can actively emit these sounds to interact with the environment, to perceive the 3D spatial layout of their surroundings. And these received echoes can are rich with information about the environment. So our idea here is that we want to leverage echolocation for feature learning. It's different from kind of traditional self-supervised learning that aims to learn generic features, generic visual features, and usually from maybe large scale data. Differently, our goal here is that we want to learn features that are suitable for tasks that require spatial reasoning, such as monocular depth prediction, surface normal estimation, and visual navigation. And the key insight of our approach is that we can learn useful visual features via echolocation, where the supervision comes from interacting with the physical world. And this figure illustrates the top-down view of one Facebook replica scene where the agent's location is marked. So we can see that the agent can emit 3 milliseconds, 3 omnidirectional sweep signal to get echo responses from the room. And the right column here shows a corresponding RGB image, the depths of the agent's view, as well as the echoes received in the left and right ears when the agent faces one of the 4 directions. You can see that there are subtle differences in the left channel and the right channel of the spectrograms, which are very important to convey the geometry of the space. So the agent has different views and receive different echo responses in the other 3 directions. So this is the data we have. So before I introduce our self-supervised feature learning method, we first perform a case study to investigate the spatial cues in echoes. So we're interested in 2 questions. The first question, can we predict depth maps purely from echoes? So we design an echo to depth network that only takes echoes response as input, trying to predict the depths of the surface. We also do RGB to depths, basically taking an image of the agent's view, trying to predict the depths. So this RGB to depths model represents the existing molecular depth prediction approaches that predict depths from a single RGB image. And I also have the RGB plus echo to depth network, because we're interested in the second question we're interested in is that can we augment monocular depth estimation using echoes? So this RGB plus echo to depth network takes the echo responses and the corresponding egocentric RGB view as input and perform joint audio-visual analysis to predict the depth map for the input image. So the other settings are the same for these 3 networks. And the goal here is that we want to find out the extent of the spatial cues contained in each modality. So here are some quality results. We're predicting the depth map for the scene shown in the left column. And here is the echo-only results. You can see that for echo-only, we can predict the surfaces. It confirms that the echo can inform about the depths, and it can capture the rough room layout, especially in this maybe large surfaces. And here is the result for RGB to depths, which is more accurate than echo to depths. And this is RGB plus echo to depths, which gives more accurate predictions. We can see that in row 1, the RGB only model, it mistakenly infers the strong contours for the column on the back wall to indicate a much closer surface. Well, for the RGB plus echo model, it infers the depths correctly. It infers much better for the depths on the back wall with the help of this additional spatial cues from the echoes. And quantitatively, we have similar observations. Echo to depths performs better than the average baseline, which always predicts the average depth map of the training set. Okay. And remember that our goal here is that we want to use echolocation for feature learning. So next I will describe our key idea, a framework of self-supervised representation learning visual echoes. So firstly, the agent's current RGB view is used as input to a visual network. And at any position in the scene, we suppose the agent can face 4 orientations, right? So when the agent emits the 3 millisecond sweep signal at a certain position, it will hear different echo responses when it faces each different orientation. So we use an audio stream that takes the echo response received from one of the 4 orientations. It can be the same orientation as the agent's current view. It can be the orientation if the agent turns right by 90 degrees. It can be the opposite orientation to the agent's current view. It can be the orientation if the agent turns left by 90 degrees. So then we use an audio network to process the binaural spectrum of the echo response, and combining using an audio video fusion module, we predict which direction the agent receives the echoes. So if the agent can correctly interpret the spatial layout of the current view from just the view information, it should be able to tell whether the visual input is congruous with the echo response it hears, right? So since these 4 classes are defined relative to the agent's current view, so the agent can only tell the orientation for which it is receiving the echoes if it can correctly interpret the 3D spatial layout within the RGB input. So in this way, the agent's oral interaction with the scene can enhance spatial feature learning for the visual stream. So finally, we obtain this visual echoes net of the learned spatial representation. I want to stress that our method hears echoes during training only. At test time, it uses only the image input, and the visual echoes encoding for RGB images alone benefits from prior audio spatial learning. So as I mentioned, we evaluate on 3 tasks: monaural depth prediction, surface normal estimation, visual navigation. Across the 3 tasks, our visual echoes features are competitive or even better than supervised pre-training. So these results consistently show the promise of the visual echoes features. We can see that learning from echoes translates into a strengthened visual encoding. Okay, any questions so far? So yeah, just now I'm mainly focusing on the spatial cues of audio related to the 3D environment. Record that another important factor is in spatial perception of audio is that we have 2 ears. We receive this 2-channel binaural audio to perceive spatial information, but the spatial effects are absent in monaural audio. Right? So next, I want to briefly talk about another idea. We have just 2.5D visual sound. So our idea is that we want to lift the single channel monaural audio to binaural audio, which has both the left channel and the right channel to mimic human hearing. And we achieve this by leveraging the visual cues in videos. Although we cannot sense the locations of the sound sources by listening to the mono recording, the accompanying visual frames of the monaural audio do contain the object and scene configurations, so we can anticipate what we would hear if we were personally in the scene by inference from the video frames. However, binaural recordings are scarce, so we collect a new video dataset with binaural audio. So we assembled a data collection rig with a GoPro camera attached to a binaural microphone. It mimics human hearing and records signals received in both ears separately. Note that both the shape of the two ears and their spatial separation are significant to simulate the physical manner in which humans receive sound. And we have this binaural microphone, and we capture about 5 hours video and binaural sound in the music room. And we call this dataset fair play. Then I'll describe our approach, 2.5D video sound. We formulate a self-supervised learning task. So given this data, we have this left channel audio, right channel audio. So we first mix the two channels to get a mono audio. So now the spatial information collapses. So then we can get audio spectrogram from mono audio. Although we don't have the spatial information maybe in the mono audio, but we can, the video frames also contain the spatial cues. So we design a mono to binaural deep network that takes the audio spectrogram and the visual frame as input, trying to predict to predict left channel, right channel. And at test time, we only need a mono signal as input to infer the 2.5D visual sound. Now let's see some results. Unfortunately, the spatial effects can only be perceived when listening with headphones. When you listen with the speakers from my laptop, it will actually sound flat. But with a headphone, you can feel the spatial effect. Here, I'm just going to show a sample result. We show the input monaural audio and the predict binaural audio signal using our method, as well as the ground truth binaural audio. So we also have performed a user study to help you understand what has been learned. We have demonstrated that, I want to demonstrate that when listeners listen to the binaural audio inferred by our method, they can indeed sense the locations of objects in the scene. And the listener does not see any video in the user study. We ask the listener where is the drum and the piano in the video. And the heat map here shows the perceived locations of the drum in green and the piano in purple from the listeners. We can see that it pretty accurately captures locations of the objects when listening to the predict binaural audio. So also our user study confirms this. It outperforms the baselines and matches to the ground truth. Okay, yeah, I know I'm maybe a little bit out of time, but yeah, I have maybe a final kind of work I can briefly introduce. But if you want to stop me, please feel free to stop me at any time for any questions. Yeah, but otherwise I'm happy to continue.
Yeah, I would say go ahead and continue.
Okay. Yeah. Yeah.
We have the buffer zone for those who want to stay.
Okay. Cool. So yeah. So in the final kind of project I want to show, I want to actually revisit this example of where we started today. Yeah. So you can see that I show that there are visual information, the appearance of the objects. There are audios. There are sounds made by these objects. There are many objects in the scene. We can see, we can hear, but one thing we are missing is that we can also actually touch, right? So the baby is interacting with the eyeglasses using its hand. So from manipulating or interacting with object, we can the baby probably can tell, maybe you can also learn that maybe the eyeglasses is plastic. Maybe it can do instance recognition to tell that this is an eyeglass. And it knows that it's graspable from the arm of the eyeglasses, and maybe it can feel that it's hard in terms of material. So modeling objects is very important, and perceiving these objects often needs multisensory input, right? So finally, I will introduce our latest effort to build a data set of objects that indeed contains all of these multisensory signals: vision, audio, and touch. So actually, multisensory object-centric perception, reasoning, and interaction have been a key research topic in recent years. However, existing data sets of synthetic objects such as ShapeNet are unrealistic and focusing purely on object geometry. And real object data sets such as YCB are often practically challenging and unstable to acquire due to maybe international shipping, inventory, and financial cost. So that's why we want to introduce Object Folder, which is a data set that contains 100 object files in the form of implicit representations. So each object file in this Object Folder dataset is a neural network. It contains a complete multisensory profile for an object instance. So querying each object file with the corresponding extrinsic parameters, we can obtain realistic object-centric, visual, auditory, and tactile sensory data. So the main contributions of Object Folder as follows. We basically propose a uniform, object-centric, and implicit representation for each object. And this dataset is easily accessible to the community as a standard benchmark for multisensory learning with vision, audio, and touch. And these objects are compatible to different robotic virtual environments. So this is the implicit neural representation network, and we call it object file. So each object file implicit neural representation contains 3 subnetworks: VisionNet, AudioNet, and TouchNet, and which through querying with the corresponding extrinsic parameters like 3D coordinates, light direction, spectrum location, tactile map location, we can obtain the visual appearance of the object from different views, and impact sounds of the objects at each position, and tactile sensing of the object at every surface location, respectively. So I'm just going to quickly show some examples of different modalities. Here is a glance of the object of the 100 high-quality 3D object, and we try to render the object's appearance, the vision, from different camera viewpoint. Here are the 100 objects we have. And here we are rendering these objects varying the lighting directions. So this is for vision. So for audio, here's an example of a black bowl where the material type is ceramic and the scale is 0.16 meters, and we try to get the audio from the object file. Here are the impact sounds we can get by querying object file implicit representation. Here's another example of a slice of a toaster. This is for audio, and for touch, we use a digit sensor to touch different locations of objects. Here is what we can get from our implicit representation. For this plate object, the right side shows the tactile image obtained by touching different locations. Here's another object, medicine bottle. It's touching different locations of the object. We can obtain the tactile readings by querying our implicit representation network. Okay, so what can Object Folder be used for? So it is a potential testbed for many machine learning and robotics tasks require multisensory perception, and we have evaluated on 4 benchmark tasks, including instance recognition, cross-sensory retrieval, 3D reconstruction, and robotic grasping to demonstrate the usefulness of the dataset and the value of multisensory perception. So I will skip the details of the results. Here we did instance recognition to identify the object based on its visual appearance, impact sound, or local contact geometry, and cross-sensory retrieval to retrieve different modalities, and 3D reconstruction, and robotic grasping. So here are some just examples of how we can use our dataset for multisensory perception and control. Okay, To summarize today, yeah, I talked about how we can disentangle object sounds from video and robotic interactions, how we can use audio as an efficient preview for video action recognition, how we can infer binaural audio from monaural audio by learning from videos, and how we can use echolocation to learn spatial image representation. And finally, also talk about our latest work on an object-centric multisensory dataset in the form of implicit representations. And the work I talked today, I joined work with the people shown here. So with that, I will conclude my talk, and I'm happy to take any questions. Yeah, thank you.
Thank you, Ruohan. That was great. I assume that everyone who is still here is a big fan of the work and interested. So are there any other questions?
Can we have a time to have a questions offline? Gordon.
Yes, yeah, absolutely. If no one else has any questions about the talk, we can move on.
Yeah, I can ask a question. Can I?
Please, Anu.
Oh,
yeah.
okay. Hi, excellent presentation, and I'm a big fan of your work. And we have been following up on some of your past efforts on audio-visual separation, and so my question is on this the data set that you mentioned, like implicit representation stuff. So how is the ground truth generated for touch and sounds and stuff? Like how did you generate it?
Yeah, so for audio, yeah, thank you for the question. Yeah, so for audio simulation, basically we do model analysis based on the shape and the material and the scale of the object, so that we can simulate the sounds for each vertex of the object mesh, and then we can use a implicit representation network to encode the simulated audio. So the ground truth is still based on simulation. For audio, for touch is also based on tactile simulation. We used one of the state-of-the-art tactile simulation framework from Tactile. It's called Tactile, and we get the touch simulation ground truth or pseudo ground truth for each vertex on the object, and then we also use the touch net to encode the representation. So that's how we kind of get the ground truth. It's not definitely there may be still a seam to real gap, but that's kind of the ground truth we get to encode to learn the implicit representation network.
But that kind of disentangles the different modalities, right? Like, I mean, if you want to touch and hear the sound, how is that possible? I mean, you want to like maybe poke the object, and so there is a touch as well as you want to hear the sound. Is that also plausible to be acquired with the data set, or?
Yeah, it's a unified representation. So for each vertex, we can obtain its audio and its touch. Okay. Yeah, but it's kind of the simulation is separate.
I see. Okay. Yeah. I see. Okay. And I have another question regarding your work on the interactions, like when that robot was like using the spoon to get the material. I mean, so I was wondering, like, is classification the right task for that kind of a thing? Because it's the same spoon, and so you can basically marginalize out the spoon sound from the object that it is interacting with if you have examples for training. So is that the right task to show sound separation quality while you can directly classify materials by directly using the spectrograms is what I feel like. So I'm just trying to understand why the classifier performance without the audio separation was so bad. Was the features getting somehow intermixed with the sound of the spoon that some information is lost? If that is lost, then the system has to generate it, right? If you want to, yeah. So why is the classifier not performing well in that case? If you don't have a separated audio, what are your thoughts on that?
Right. Yeah. So yeah, as I mentioned, basically the classification kind of is a proxy. It's not a very maybe interesting task in itself, but it's a proxy to evaluate the separation quality. And for the my intuition is that because for the mixed audio, it's like a different objects. If it's a tool, it's a steel fork and a ceramic mask. Right? You only have the mixed audio. Then it's a mixture of two materials, right? If I want to directly classify based on this mixture sound, then a classifier can make mistakes because there are two materials mixed in each other. So I don't know how should I classify the material of this mixture sound. But if I do separation, then it's only one material. Now I can do a better classification. You want to do material classification because the classification we did is material classification. So that's why it can enhance the performance.
Yeah, but still, it's the same spoon, like you said. Like you're not changing the spoon, and if the spoon changes, then I mean the harmonics changes, then the separation might be harder, perhaps. So if it's the same object that you are going to impact with the different objects, then I'm kind of thinking like, why is the classification so hard? I mean, you probably can. You just need to know the material. You have to just classify among the set of materials, right? Ultimately, so won't that just happen from discriminative learning than going through a separation and then discriminative learning? Maybe, yeah, I don't know. I mean, it's also just kind of trying to figure out why it was working.
Yeah, really get your kind of question. Yeah, but we have different kind of objects of the same material, right. And then we have a different steels, different forks, for example, different kind of tools. So that's can be when doing material classification, if it's mixture audio, so it can cause some confusion there. So
I see.
Although but still, I think if we have kind of a larger data set, that might be more.
I see.
Solid in terms of the results. Yeah.
Okay. Yeah, that makes sense. Yeah. Okay. Great. Thanks.
Yeah. Thanks. Yeah.